So consider a structure AB, okay, indeterminate structure. Then the deflected shape being like this, okay, theta A with the tangent. Then the slope deflection equation is fixed end moment AB plus 2EI by L, L being the span of this 2 theta A plus theta B minus 3 delta. Okay, so this is the slope deflection equation. And for BA, fixed end moment when end B is kept fixed, 2EI by L theta A plus 2 theta B minus 3 delta L. So this is the slope deflection equation, where delta is the deflection, okay, or displacement, theta A is the angle or rotation of the end A, theta B being the rotation at angle at end B, L being the length of span, fixed end moment AB, that is keeping one end fixed, and the moment due to restraint is known as fixed end moment, okay, FEMAB, and it depends upon the loading. If and only occurs if there is a loading at the member, not at the joint, okay. For example, if I have a loading over in this joint, then it doesn't cause fixed end moment, okay. So it has to be in the member. Let's move into a numerical now. So for this displacement method, you have to keep some points in your mind. Fixed end moment AB, okay, as I will discuss, this is a very important term in displacement method, okay, that is fixed end moment. The second is case of a fixed support, okay, the rotation takes at a distance from the fixed support, okay. So theta is 0 for fixed support. This point has to be considered because substituting this value at point in the equation, okay. And the next is the direction or the sign of the displacement. For example, I have a support A and B. If the support A settles down by some value like 3 mm, okay, then the value of the displacement should be assumed, the value of deflection, okay, deflection should be taken with respect to the sign made, okay. For example, here the sign made with the horizontal is anti-clockwise, okay. So theta is equal to negative, that is you have to put the value here delta as negative. So delta is taken as negative, so negative negative plus, okay. And in the case also, if it is provided with for example, A settles by 3, B settles by lifts up by some say 2, okay. Now the overall deflection or displacement is this total, so 2 plus 3 is equal to 5 mm, okay. You have to consider this point, and you can do the numerical related to slope deflection. So this is the question for slope deflection method, okay. You are provided with a 3-span continuous beam, and also the condition of deflection, okay, displacement, that the left middle support B, left middle support settles 2 mm downward, okay. This support settles downward, and the right middle support lifts 3 mm up. So this C support lifts up to 3 mm. Now the question is to analyze the given beam using slope deflection method and draw BMD for the beam. Take EI is equal to 8 into 10 to power 11 Newton per mm square, okay. So using slope deflection method, we have to go through 3 basic steps. The very first step is to calculate fixed end moment. Okay, calculation of fixed end moment. Okay, so member, there are AB, BC, CD, and according to that BA, CB, and DC. So for fixed end moment of AB, we have the formula. It is a UDL. Okay, and for UDL, the moment is given by WL square by 12, negative sign because we are moving from left to right, and gives a anti-clockwise moment, okay, towards B. So minus 2 multiplied by L is 6 square by 12, we get minus 6 kilonewton per meter. Fixed end moment BA, now WL square by 12, okay, gives a clockwise moment here. And the value will be positive 6 kilonewton per meter. Fixed end moment for BC, for point load, okay, the formula for determining the moment is WA square by L square. So minus WAB square by L square, so we get minus 2.4 kilonewton per meter, kilonewton meter. Okay, then FEM CB, again WA square B by L, because now we are moving from here, WA square B by L, and we get 3.6 kilonewton meter. Okay, so 3.6 kilonewton per meter is for CB. Now moving to CD, fixed end moment for CD member, again a point load, so WAB square by L square. Now you can make a point formula, okay, for a point load acting at the mid span. So if you see A and B are equal, that is 2.5 meter, 2.5 meter, so A is equal to A, and basically A is equal to L by 2, so W into L by 2 into L by 2 square by L square. So on calculation we get WL being square, it will get cancelled out, so WL square by 2 square 4 into 8. So for for point load at a mid span of the member, the fixed end moment is given by WL square by 8. Okay, negative sign because we are moving from left to right. W is 8, so minus W8 into length is 5, then we get value as minus 5 kilonewton meter. Okay, for DC it will be same, just with a negative sign being removed, we get 5 kilonewton meter. Okay, so the very first step, that is calculation of fixed end moment, is done. Now the next step is to find slope deflection equation. Okay, and the slope deflection equation, as I have already discussed earlier, for AB member MAB, it will be fixed end moment of that member plus twice EI by span length by 2 theta A plus theta B minus 3 delta L, where delta is the deflection. Now you have to make a note. Left middle support settles 2 mm down. So let me make a figure here. Okay, this support settles down. Okay, this being A, B and B dash. Now the support has settled down by 2 mm. Okay, and makes a clockwise angle with the displacement, so the displacement is taken positive here. Okay, now substitute the value. Fixed end moment for AB, it is minus 6 plus the stiffness of the member is EI, so 2EI by L is 6 meter. Theta A, it is a fixed support, so for fixed support, if we see, the deflection goes like this, okay? So theta A is 0, that is for rigid. For a fixed support, theta, that is rotation, is 0. Theta B, it is an intermediate member, so it will have a rotation, and theta B minus 3 delta into L. So we can substitute the value for delta here, okay, which is 2 mm. That means by converting it into meter, we get 0.002 meter, okay. So 3 multiplied by 0.002 by the length is 6, okay, minus 6 plus 3 minus 6 plus 2EI 3, theta B minus 3 2, so we get EI by 3 theta B minus 0.001, equation number 1, okay. Now for BA, just make a trick, okay, you can work on it. Fixed end moment for BA plus 2EI by L, always put twice for the precedence in this term, okay. So 2 theta B plus theta A minus 3 delta by L, okay. Fixed end moment BA, we have calculated it, 6 meter, sorry, 6 kilonewton meter. 2EI by 6, 2 theta B, theta A will be 0, minus 3 into displacement is 0.02, so 6, and we get same to this but with some change in negative sign. EI by 3, 2 theta B 0.01. We can see some changes in these two equations. Now for BC, okay. In BC portion, fixed end moment, now I'll not write the formula, I'll just put out the value, okay. So fixed end moment for BC is minus 2.4 plus 2 into 2 EI, because the stiffness is twice EI, so 2 into 2 EI, the span length is 5. Now both are roller, so it will have some rotation. 2 theta B plus 2 theta C minus the displacement, okay. Now you see both of them are displaced, okay, and if we see the net displacement is this being 2 mm downward and this being 3 mm upward, so the overall displacement here is 5 mm, okay. The overall displacement is 5 mm, and the sign, if you see, okay, the sign, if you see, is anti-clockwise, okay, is anti-clockwise, sorry, it is anti-clockwise by making with the tangent. So for anti-clockwise we take displacement as negative, so the overall displacement is 5, okay. If both were in the same direction, the displacement would have been different. For example, if it has displaced by 3 mm downward and this also displaced downward by 5 mm, then the overall displacement would be 2 mm only, okay. But in this case both are in the opposite direction, the net displacement will be 5 mm here. So 3 into minus 0.005, okay, L being the length, so L is 5 here, okay. So we can calculate the value now just by performing some calculation. Minus 2.4 plus 4 by 5 EI 2 theta B plus theta C minus minus plus, so 0.003, equation third. Similarly, you can calculate MCB, which is 3.6 FEMCB, okay, 3.6 plus 2 into 2EI by 5. Now C is in the precedence, so 2 theta C plus theta B minus the displacement is negative 5. Okay, now calculate it and we get 4 by 5 EI 2 theta C plus theta B plus 0.003. Similarly, MCD, okay, FEM, that is fixed end moment, is minus 5. Now again the displacement, here you can see this C settles, sorry, this being C which goes upward, okay, sorry, C dash by 3 mm, and we see it makes a clockwise angle with the tangent, okay. So this becomes positive theta C, okay, minus 5 twice EI, that is, for this EI is constant, that is EI only, so 5 meter, 2 theta C in the preceding, so 2 theta C plus theta D minus 3 into, this is clockwise, okay, this is clockwise, so we will put positive value for displacement, so 3 into 0.003 divided by 5. So we get the value as minus 5 plus 2 by 5 EI 2 theta C minus theta D, again it is a fixed support, so theta D will be 0, minus 1.8 into 10 to the power minus 3, equation number 4. And finally MDC, okay, from MDC you can see we have calculated the fixed end moment to be 5 plus 2 by 5 EI 2 theta D, theta D is equal to 0 for fixed support, so 0 plus theta C minus 3 delta by L, that is 1.8 into 10 to the power minus 3, and we get the fifth equation. So equation number 1, 2, 3, 4 and 5, okay, and this is sixth. So we have total 6 equations. Now applying the joint equilibrium condition, we can calculate the moment, okay. So let me make a figure over here. A, B, C and D, okay. At joint B we can apply the joint equilibrium condition, okay. So what actually joint equilibrium condition is then? Joint equilibrium condition says the moment about the left portion and right portion of a point is equal to 0, okay. So we will not apply it at point A and B because it is a fixed end and it will have some moment, okay, it won't be 0. But in case of this, the summation of moment in the left portion and the right portion will be 0. So MAB plus MBC is equal to 0, that MBA and MBC is equal to 0. Now bring out the equation we had, okay. So BA, that is 6 plus EI by 3, 2 theta B minus 0.001, and MBC being minus 2.4 plus 4 by 5 EI 2 theta B plus theta C plus 0.003. So 6 plus 2 EI by 3, 2 theta B minus 0.001 EI by 3 plus 8 EI theta B by 5 plus 4ei theta c 5 plus 0.012 ei by 5 minus 2.4 is equal to 0. Okay, it is on further simplification I got this value. Okay, on simplifying, 90 plus 10 ei theta b minus 0.005 ei plus 24 ei theta b plus 12 ei theta c plus 0.036 ei 36 is equal to 0. Okay, and finally I get 34 ei theta b plus 12 ei theta c minus 78.8. So don't put out the value of ei directly over here. Okay, it will be much more complex because the value will be large, so it is better to put the value of ei at last. Okay, now at joint C, okay, for joint C we had MCB and MCD. Okay, MCB being 3.6 plus minus 3 plus 3.6 4 ei by 5 2 theta c plus theta b plus 0.003. okay, plus MCD now minus 5 plus 2 ei by 5 2 theta c, theta d was 0, so 1.8 into 10 to power minus 3 is equal to 0. So this is the joint equilibrium condition at C. On further simplification, okay, I get 4 ei theta b plus 12 ei theta c is equal to 0.28. Equation A and equation B. On solving equation A and B, okay, these are two equilibrium simultaneous equation for theta b and theta c. On solving ei theta b, I found it to be minus 2.636 and ei theta c as 0.902. okay, theta b, okay, minus 2.636 by, we are provided with 8 into 10 to the power 11 Newton mm square, and we have to convert it into kilonewton meter square. So for which 8 into 10 to the power 11, okay, by 1000, and mm square will convert it into meter square. 1 divided by 1000 to power square, we get 800 kilonewton m square. Okay, 800 kilonewton meter square. So 800 ei, okay, and we get minus 3.29 into 10 to power minus 3. And similarly here, theta c is equal to 1.127 into 10 to power minus 3. Now substitute value of theta b and theta c respectively in equation, then we get the value of MAB. So MAB is equal to minus 6 plus 800 by 3, that is value of ei, okay, in this case ei, into 3. Value of theta b is minus 3.295 into 10 to power minus 3 minus 0.001, so it becomes minus 7.145 kilonewton meter. Okay, similarly for MBC, we can calculate it as MBC minus, MBA, we have to calculate MBA first. Okay, so 6 plus 2 ei is 800, theta b we have calculated, and substituting the value, okay, 6 plus 800 by 3, okay, 800, that means 2 ei and 3 calculated, so 2 being here 6 and up 6, so of 2 and 6 we get 1 by 3. 800 by 3 minus 2 multiplied by 3.925 multiplied by 10 to the power minus 3, 0.001 is equal to 3.976 kilonewton meter. Similarly, keep on substituting the value of theta b, theta c, theta c, theta b, and theta c. We'll get the value of all other. Okay, so mbc is equal to minus 3.97 kilonewton meter. mcb is equal to 4.85367 kilonewton meter. mcd is equal to minus 4.857 kilonewton meter, and mdc is equal to 4.786 kilonewton meter. And you can see mba and mbc is same with the opposite sign. That implies the condition to be true, that mba plus mbc is equal to 0. Similarly, mbc plus mcb plus mcd is equal to 0. So there is a change in the sign only. Now the question has asked us to analyze the structure with slope deflection equation method and determine the bending moment diagram. Okay, so bending moment diagram. Copy the structure. Okay, so you are provided with this A, B, C and D. Okay, MAB, you will take the, we are moving from left to right, so always choose the left to right portion only. So that is MAB, BC, CD. So MAB, it has a moment of minus 7.1425. So considering the upward positive, okay, considering the upward positive, MBC and MCD. Okay, MAB is minus 7.145. So minus 7.1425. For BC we have minus 3.97. For CD we have minus 4.857. And for DC we have 4.786. Okay, 4.786. This is the first part of bending moment diagram. Now we have to determine the maximum bending moment at each portion. So if we see in AB, it has a uniformly distributed load. For BC, a point load, and for CD it has a point load. Now maximum bending moment over this span. Okay, first UDL, that is AB portion, the formula is WL square by 8. Okay, and we have W as 2 kilonewton per meter and L being 5. Okay, L being 6 square divided by 8, that is 9 kilonewton meter. The second is for BC, that is a point load, and the formula is WAB by L. Okay, so W being 5 kilonewton meter, A being 3, and that 2 divided by 5, we get 6 kilonewton meter. And for CD portion, again WAB by L, W being 8, 2.5 multiplied by 2.5 divided by 5, 8 multiplied by 2.5 into 2.5 divided by 5, we get 10. Okay, now plot this maximum value at the center span. Okay, so 9, it should be somewhere here. It is a UDL, so it will be a curve. Okay, it is a curve. For BC, a point load 6 kilonewton meter, this being BC minus 3 and this being minus 4, so 6 kilonewton meter. So for this we will put the positive value upward, okay, and for this negative value upward. So BC is equal to 6, point load, so it is a straight line. For the case of this also, it is a point load, it will be a straight line, maximum at the center. But in this case for BC, it will be maximum at the point of application of load. Okay, for point load it will be maximum at the point load application. So now hatch the non-overlapping portion. Okay, so this is a non-overlapping portion, this is a non-overlapping portion, this is a non-overlapping portion, this is a non-overlapping portion. Okay, so this is negative part, this is positive, this is negative, this is positive, negative, positive, negative. Okay, this being 9, this being 6, this being 10. This is positive because it is a positive value, and this is the negative portion. Okay, so this is the bending moment diagram for this structure. I hope you have understood this method. Any queries, do comment, and you can ask me any question in the comment section. Thank you.